Okay, so we are going to continue talking about the Metropolis algorithm. Okay. And the way the Metropolis algorithm works is you have a target distribution. Okay, so you desire to generate samples of random values from a target distribution. We'll just say P of x, okay? So P of x is some PDF. PDF or PMF, I guess, if it's a discrete. So it could be discrete or continuous. This is what you desire. You desire to generate samples from a target distribution, okay? And at least in the discrete case, we propose, we are currently at some value, okay? So at each iteration, okay, or I guess for the Metropolis algorithm is, we then we run a Markov chain, okay, and at time t, our current value is x at time t. Okay. So we're currently located at some value, and in the island hopping thing, we were located at island 4, island 6, wherever we are. Okay, that's our current value, x at time t. And then we propose a new value using a proposal distribution. Okay, and the proposal distribution for the Metropolis algorithm has to be symmetric. Okay. We'll learn about the Metropolis Hastings algorithm where it does not need to be symmetric, but we propose a new value using a proposal distribution, okay? And so for the island hopping example, okay, our proposal distribution looks like this. Okay, we propose x of t plus 1 versus x of t minus 1 with a probability equal to 0.5 and probability equal to 0.5. Okay, so wherever we are now, if we're at island 4, the proposed values are either going to be 5 or 3, okay? If we're at island 1, our proposed values are either going to be 2 or 0. Okay, so that's what we have for the island hopping example. In general, okay, I forget what letter we should use. Let's just call it G. Okay, in general, and I apologize if the notation, the letters change in the future. But in general, we might say our proposal distribution is g of x given x at time t, okay? Because it's a Markov chain, the next value, the value you're going to propose, depends on your current value, right? So in our island hopping example, the islands we propose next, the values we propose next, depend on our current location. If we're currently at located at island 2, the values we might propose are different. They're going to be 3 versus 1, okay? If we're at island 6, I might propose island 7, I might propose island 5, okay? So it depends on your current location x at time t. You know, other examples, so for like a, and I guess we'll explore this in the future, but so you can have, you know, for the discrete case, exactly what we have, g of x at time t for discrete case example will be x is going to be x at time t plus 1, time t plus 1, or x at time t minus 1, and then g of x given x at time t. These are, you know, this is exactly what we have. This is the island hopping example. Okay, you know, possible continuous proposal distribution would be, you know, x comes from a normal distribution where the mean is equal to your current value and standard deviation sigma. So you could propose a random x from a normal distribution where the mean is set to the current value. Okay, so we can see how the values we propose depend on our current value. That's kind of a key factor in Markov chain Monte Carlo, is that, you know, future values depend on your current value. The next value depends on your current value, okay? You know, let's say I wanted to have a uniform proposal. What would a uniform proposal look like? So another possible continuous distribution. Okay, we could say x comes from a uniform where the lower bound is going to be x of t minus, say, 1/2, to the upper bound will be our current value x of t plus 1/2. Okay, and that would produce, you know, new random values centered at our current location and what we propose, right? So the Metropolis algorithm requires that our proposal distribution is symmetric, okay? Okay, so what this means the probability of proposing, let's say, x sub, we'll call it x super a, if, or I should say x super b if we are at x a, is equal to the probability of proposing the opposite. Right? Or we might say g of xa given xb is the same as g of xb given that we're at xa. So if we're at one spot, the probability of proposing this other value is the same as if we're over here and the probability of proposing our current value. So, you know, for the island example, it's the case, right? So this is true for island hopping. Okay, so if we are at island 3, we propose island 4 with probability equal to 0.5. And if we are at island 4, we propose island 3 with probability equal to 0.5. Okay, because in order to propose island 4 on island 3, you have to flip heads, which happens with probability 0.5. And in order to propose island 3, if we're at island 4, we have to flip tails, which also happens with probability 0.5. So that's going to be symmetric, right? And then also because, you know, the normal distribution is symmetric, you know, the probability, like if we're currently at 0, the probability of proposing, you know, 1 is going to be the same as if I'm at 1, what's the probability I propose 0? Okay. So all of those things. Is that okay? The idea of a symmetric proposal? So anyway, so again, going back to the Metropolis algorithm. So, you know, we are at x at time t, okay? We propose, so I'll do x star, which comes from our proposal distribution. Okay, and then we calculate the probability of moving, which is going to be equal to the probability of the proposed value, P of x star, x proposed, divided by P of our current value. So just, and this P comes from our target distribution, okay? These values, P of x star and P of x at time t, come from the target PDF or PMF. So your target distribution, that's what's going to determine the P of x, okay? And basically what it says is that if the proposed value is more likely than the current value, you will definitely accept and move to that location, okay? So if the proposed value, x star, is more likely than the current value, definitely accept and move there, okay? The current value being xt. And if the proposed value is less likely than the current value, okay, then you say, well, maybe I'll go, maybe I won't, okay? And then it depends on the ratio between how likely the proposed value is to the current value. Then maybe you go, maybe not. Okay, and it depends on basically the relative probabilities. Okay. And if you go, then x at time t plus 1 becomes your proposed value. You use the proposed value as the next x value. And if you don't go, you just reuse your current value. All right. And that's the Metropolis algorithm, okay? Let's take a look. Let's revisit the island nation and see if we can get this to work, okay? All right, so island nation. All right, so the target distribution is going to be basically 1, 2, 3, 4, 5, 6, 7. These are our nations, our islands. And this is going to have probability 1 over 28. So this is P of x. This is our target probabilities. Okay. An interesting thing about the Metropolis algorithm is that we don't actually need the normalizing constant in the bottom, okay? So I took all of these numbers and I divided by 28 so that they add up to 1, okay? But in the Metropolis algorithm, because your probability of moving is the probability of the proposed divided by the probability of the current, if there is a normalizing constant in both of those cases, they're going to both be canceled out. And so you don't actually have to calculate that, right? Which comes in very handy when we're doing Bayesian methods, because in Bayesian methods, that marginal probability that sits in the denominator is often very difficult to calculate, and so that ends up going away. But you know, I'll talk more about that. Okay, but okay, so here's our algorithm. begin at some island. Okay. Propose a new island with the coin flip. Okay, so we'll say begin at some island, x at time t. Propose a new island with the coin flip, so either x one more or one less. Okay, and then find probability move is going to be equal to the smaller of 1 versus p of x star versus probability of the current, and then x at time t plus 1 will equal x star if we accept. Basically, if u, so we'll say u comes from uniform 0, 1, if u is less than p move, and x at time t plus 1 will be our current xt if we reject u is greater than p move. Yeah. Okay. And that's the entire Metropolis algorithm. Does that kind of make sense, the process? All right. Shall we code this up? See how this is done? Okay. Okay, so let's just create something called target, and this will be the values 1 through 7 divided by 28, okay? I don't know what that means. Okay, so let's just print out what is this? Why are you complaining to me? Okay, let's just restart R. Okay, it can't, it's having problems. Okay, let's try this again. New R script. Okay, so we'll say the target is going to be the values 1 through 7, I guess divided by the sum of 1 through 7. Okay, and so I can just ask for what does the target look like. Okay, this is 1 over 28, 2 over 28, 3 over 28, 4 over 28, 5, 6, 7 over 28 is 0.25. I don't know if, can you guys see that at all? Here, okay. So there is, that's our target distribution, okay? So I'm going to write a function for propose, function of x, and basically we'll just say u is our unif 1. We're going to pull a random uniform, and I'm just going to do if else. If u is less than 0.5, then what we want is we want to propose x plus 1. Otherwise, we'll return x minus 1. Okay, is that all right? Does that make sense for flipping a coin and return a value bigger than x, 1 bigger than x, or 1 smaller than x? So that's going to be my function propose. So I just say like propose, and if we're at 4, it's going to say let's go to 5, or let's go to 3, or let's go to 5, or okay. And if I'm like at island 1, we'll propose 0 or 2 or 0 or 2. Okay. Is that okay? So that's my function propose. All right. So let's write our loop, which will be, let's just do for I in, I don't know, 1 through, how many should I do? 100,000? Okay, that sounds good. And then let's, so we'll say x0 will start off at 4. At time 0, we'll start off at 4, and then we'll say my results will just be an empty vector of 100,000. Okay, so I'm going to call x star is going to be, we use our propose function based on our current x. So I should say, yeah, okay. Oh, here, this is what I should do. Results, our first result will be x0. Okay, so we're going to propose based on our current results spot I. Is that okay? So looking at what's currently in results, so the very first value is going to be 4. So looking at that, we're going to propose a value x star based on this. Is that okay? All right, and then p move, so will be the minimum between 1 and, let's just call this p ratio, and we'll calculate p ratio separately. So p ratio, this is the probability of the proposed value divided by the probability of the current value. Okay, so what's the probability of the proposed value? How would I get that? I can just say target of results bracket I, right? Divided by, I'm sorry, not results bracket I, this is x star, divided by target results bracket I, because this is my current value. Maybe for clarity, I'll just call this x current. I don't know if any of this is helping. So we'll call this, if I say the current result is x, this is just for your clarity, okay? So I'm going to propose based on the current and then x current, okay? Does that make sense? So if if I say I is 1, okay, x current, it will be results I. So what is x current? X current is 4. Then I propose a value based on x current. So in that case, I proposed 3. If I run it again, my x star is 3, okay? And then if we look at the target distribution, I can get the target of the third value just by saying target 3 versus x current, which is 4, and I can say target 4, right? So my ratio will be target, the probability of the third island divided by the probability of the fourth island, and I get 0.75, which makes sense. Is that okay? Is there all of this going? Okay. All right, and then the move will be the minimum of p ratio and 1, and then u will be, we propose a random uniform, okay? And if u is less than p ratio, I'm sorry, p move, it doesn't, it could have just done p ratio, but if u is less than p move, then what do we do? Results of I plus 1 doing this wrong. Then what do we put in results I plus 1? We're going to put in our proposed value. Otherwise, what do we do? Results I plus 1 gets our current value. All right, I want you to take a moment and make sure you understand this is, we're just coding up what we've written in the Metropolis algorithm. Are there any questions on any of these lines? Okay, so we're just taking our current value. We propose a new value based on our current one. And then we compare the probabilities based on our target distribution. We calculate the probability of moving. And then if u is less than that, we're going to accept our proposed value, x star. And if not, we will reuse our current value. Okay? And then it iterates and it goes and it's going to use the next value there. And we'll go. All right. So let's go ahead and try this out. So we'll start at 4. Maybe I'll set a seed. Set seed 1. Okay. And then we'll go ahead. All right. Oh, something. There in, oh, yeah, that makes sense. Okay. What happened here? It says missing value where true, false needed. What do you think happened? Okay, let's just see what my x star is. Okay, what do you think x star is? I can tell you it's going to be either 0 or 8. Okay, it's 8. All right, and so when I did target of x star, it says I don't have a value there, right? So I have a few options for here, okay? I can, so basically what we need to do is the p ratio, if we go to island 8, we need to say it's 0, or if we propose island 0, we need to say 0, okay? And so I'll do p ratio is this, and then I'm going to just do an if-else. P ratio is going to be if else is.na p ratio. So if the current value of p ratio is na, say 0, otherwise just keep p ratio. Okay, so this will just clean up na values. Does that make sense? So because the way it goes is, you know, if I'm at island 7, I might propose island 8, or I might propose island 6. And if I propose island 6, because there's no value in the target PDF for island 8, I'm sorry, if I propose island 8 and there's no value for the target in the target PDF or PMF for island 8, it's going to give back an NA, right? So if the P ratio is NA, so I can just do is NA for like target x star, okay? And it'll say true, and if that's true, then we need to say 0, okay? Then the p ratio is 0. Otherwise, keep the current value of p ratio. All right, let's just try this again then. Okay, so now it's running. We haven't, it says 50 or more warnings. Oh, geez, okay. Maybe this is not what I wanted. Okay, let's just, I'm worried. And I'm coding on the fly here, right? So, all right, and the target x star divided by target x current, the longer object length is not a multiple of the shorter current length. Huh. Okay, well, x star should be just a constant. Is x star and x current not a constant? Let's just see. Ooh, that's not a good. Somehow we're getting super negative values. I'm doing something wrong here. We propose based on our current value. The target what is is.na target 0? I'm sorry. Oh, that gives me a logical 0. So what happens if I do a if this print hi? If what happens if you do a if logical 0? Argument is of length 0. All right, I got to think of something else. So if, okay, clean up NA values for target 8. I need something, okay. I was hoping to just use the target as this, but I think I've got to write an actual function here. Okay, so the target is going to be a function of the islands, okay, of what number that we have. And I need to have, basically, if x is 0, return 0. If x is 8, return 0. Okay, and otherwise, the value we will return will be PMF is this, otherwise return PMF of x. Okay, and I think this will clean up the issues we have. Sorry, I was just trying to take a shortcut, but let me just see. Okay, so target of 0 is 0, target of 8 is 0, and target of 7 is 0.25, and target of 1 is this. Okay, I'm hoping this works now. All right. So we're going to do target of x star all right. Please work. Okay. So we're going to start off at 4. We're going to set our seed. And x current is our current results. Propose is x star. We look at x star versus x current. Target x current p ratio. Okay, that should do it. We'll see if we get, okay, no errors, no warnings. That's a good sign. Okay. All right, let's go ahead and take a look at the histogram of our results. That looks like what we want, right? Because we want the islands to be proportional to their numbers 1 through 7. That's an artifact of the histogram. Let's just do a table of the results. Okay, and we have this. And let's just see what 1 through 7 divided by 28 looks like. Okay, so here, let's multiply that by 100,000. And we'll round it off. So, versus table of results. Okay, so that looks pretty good, I would say. Okay, this is the theoretic, what should happen. We should get 25,000, and we got 24,795, 21,429, and we got 21,399. Okay, and this is simply off of what we've done here. Okay, and we just had to write, functions for our target distribution and functions for a function for my proposal distribution, okay? Which, and the interesting thing is we can modify these functions for the target or the proposal distribution and get whatever else we want, okay? So I could have done like 7 through 1 for my target distribution, okay? And now, if I rerun all of this, then island 1 will have a proportion of 7, and island 7 will have a proportion of 1. Okay, I can ask for the histogram of the results here. Okay, so we can modify our results accordingly as well. Okay, but this is just some simple code using the Metropolis algorithm. Let me, here, I'm going to just add a few more notes here. And I just want to say, so there's a few really great things about the Metropolis algorithm. Okay. One is, you can have a terrible, like if you have a continuous distribution, like let's say if you have if you have a distribution, you can have a terrible starting location, and the Metropolis algorithm will still get you to the area of interest. So, like, if the normal distribution looks like this, okay, you can start like way out here, and you can start here, and you might propose a value right here, right? Propose this value. And the thing about the Metropolis algorithm is that it just looks at probability of the current versus probability of the proposed. And you know what? It's going to say, like, when you zoom in, it's going to be like this, right? And it's going to say, oh, the proposed value is just a tiny bit taller than my current value, and so it's going to accept it for sure, right? They're both terrible locations, right? Like here you could have z equal to -50 versus z equal to -49. And we both know, like, these would never happen in the standard normal distribution. But according to the Metropolis algorithm, it will say, oh, this is less terrible. Let's accept it. Let's accept it. Okay? This is less terrible in that P proposed divided by P current is greater than 1. So we take it. Okay? And because of that, it's going to generally keep moving until you get to a good region. Okay? And yes, you can move backwards. That's another strength of the Metropolis algorithm, is that it's not strictly maximizing. You can move to lesser locations. You just do it less often. Okay? Sorry, I'm going a little bit over. So it's not strictly maximizing. Okay. You can go to a worse location, but it happens less often. Okay, we'll pause here for now, and then we'll come back on Monday. We'll look a little bit more deeper into the Metropolis algorithm, and we'll take a look. Okay, have a great weekend, you guys.